In this lesson, we're going to talk about the definite integral and understand how that's related to Riemann sums, and then we're going to talk about the different properties of definite integrals. So the first thing is just a Riemann sum recap. So we looked at Riemann sums last time, and we know that we can make rectangles of the same width from endpoint to endpoint underneath the curve. If we add up all of those areas of all the rectangles, we get an approximation for the area under the curve. The more rectangles that we make, the more accurate the approximation becomes. So is there a way to find the area under the curve exactly? Well, you betcha. If we take Riemann sums with infinite rectangles of infinitely small width, using limits as shown below, we get the exact area, which is the definite integral. So obviously, it's not really possible to make an infinite amount of rectangles, but if we made them very small and we somehow made infinite amount of rectangles, that would equal the exact area under the curve. So we're going to use integrals for that. Okay, so here in black is a definite integral. Okay, notice that there are values. In this case, there are a and b, but they'll be numbers. That is what makes this a definite integral. So we've seen this integral sign before, and when you have numbers on the bottom and top of the signs, then you have a definite integral. Okay, so a couple things to notice here. A and b, those are called your limits of integration. The limit on the bottom is called your lower limit. The limit on the top is called your upper limit. We know the integral sign. What's inside the integral is called the integrand. So it's kind of similar to like a radical, and then what's underneath a radical is a radicand. Same type of idea. You have the integral, and then the integrand is what's inside. Then we have this like dx, and it'll be whatever variable we're using. So a lot of the times we're going to see it as x, but it could be any variable. It just has to match the variable that's being used in the function. And because we have a definite integral, our answer when we evaluate this will be a number. So integrals, well, definite integrals are used for finding the area under the curve, and we have to make sure that we pay attention to the signed area. So we've talked about this before. Signed area is going to be the area above the x-axis minus the area below the x-axis, right? So anything above the x-axis is positive, anything below the x-axis is negative. So if I have the integral from a to b of f of x dx, this is really just calculating the signed area underneath the curve on the interval from a to b. So we're just going to look at a quick example. So here's the graph of h of x, which is 3 line segments and a semicircle on the interval from -4 to 6. So if I wanted to evaluate the area under the curve, what I'm looking at here is my integral, and we can see the lower limit is -2, the upper limit is 6, my integrand is h of x, and the variable I'm using is x. So we're trying to find from this graph the area under the curve. So from -2 to 6, I can see that from -2 to +2, this whole space down here, right, that's going to be negative because it's below the x-axis. From 2 to 6, this is all above the x-axis, so that piece is going to be positive. So I would just find the area under the curve like I normally would. The area from -2 to 2, well, that's just a semicircle. So we know that a circle is pi r squared. So for a semicircle, we're going to have 1/2 pi r squared. And we can see that the radius here is 2. So when I plug 2 in, I get half of pi times 4. So I'm going to get 2 pi. But it's below the x-axis, so this is going to be a negative. And then the next piece from 2 to 6, we just have a triangle. And we can see that the base is going from 2 to 6, so the base is 4. The height is 2. So 1/2, right, this over here, 1/2 base times height. So we're going to do 1/2 4 times 2, and that's going to give me 4. And I'm going to put a positive because it's above the x-axis. So my area under the curve, or the integral from -2 to 6 of h of x dx, is -2 pi plus 4. So now we're going to look at the properties of definite integrals. So there's a bunch of different properties, and you can use them to help you simplify or evaluate different operations and different circumstances involving definite integrals. So we usually assume that the integral from a to b of f of x dx, that a is going to be less than b. So typically, we would have the smaller number as our lower limit and the larger number as our upper limit. Okay? So this would indicate that you're finding the area under the curve from left to right. So it's going from a small value to a large value. However, you can find the area of under the curve going in the other direction, so going from right to left, but you have to take the sign into account. So if you're going technically backwards, right, you're going to be negating everything you're doing. So here we have the opposite way. So if we have the integral from b to a, where the larger number is on the bottom, we need to negate it and switch it. So we always want to make sure that the lower limit on the bottom is the smaller number. So if we're given the lower number being on the top, we have to flip where the limits are and then negate it. Okay, so that's our first property. We also have another property here where what if the two limits are the same? So if a is equal to b, then the distance between the x values is 0. It's not moving anywhere. It's not going from one point to another. It's staying exactly where it is. So the integral would just be 0. The area under the curve is going to be 0 because we're not moving anywhere. All right, and then here are like the basic properties. So we have the integral from a to b of a constant is going to be the constant times the upper limit minus the lower limit. Okay, so if we have only a constant, so like the integral of 2, okay, it's going to be 2 times the top limit minus the bottom limit. And then a lot of these other ones are going to be similar to other things that we've seen. So if we're adding in an integral, we can split it up and have the first integral plus the second integral. If we have a constant that's being multiplied to our function, we can pull the constant outside the integral and then just take the integral of the function. If we're subtracting, again, we can break it up into the first integral minus the second integral. So here we're going to look at an example using the properties we just talked about. So given that the integral from 0 to 1 of x squared dx is equal to 1/3, use the properties of integrals to evaluate the integral from 0 to 1 of 4 plus 3x squared dx. So here's our given information. We're going to use that to help us. We're going to use our properties to kind of break this up a little bit. Since we have addition, we're going to break this into the integral of the first thing plus the integral of the second thing. So we've got the integral from 0 to 1 of 4 dx. So the dx is going to go with both of them. Since it's outside the parentheses, it's part of the 4 and it's part of the 3x squared. So we have this integral and then plus the integral from 0 to 1 of 3x squared dx. Okay, so let's see what else we can do here. Because we have this 3 that's a constant, I can pull it outside. So I'm going to have the integral from 0 to 1 of 4 dx plus the 3 is going to come outside of the integral. I have the integral from 0 to 1 of x squared dx. So now I have what I was given, right? I was given the integral from 0 to 1 of x squared dx, and I have that exactly here. So that is going to match here, right? These are the same thing. So now what I'm going to do is replace that with 1/3. Here I have the integral of a constant, and I know from the properties that I'm going to have the constant times the top limit minus the bottom limit. So 1 minus 0. This 3 is on the outside, and we know that this integral is 1/3. So now we have 4 plus 1, and we end up getting 5 as our answer. Okay, and then the last property that we're going to look at is how we can combine integrals that are going over adjacent intervals. So for instance, if I have an integral from a to c, and I'm adding an integral from c to b, then that is the combined integral from a to b. So I guess this is kind of not the smartest to call c as something in the middle, but right. So if I have an overall interval from a to b, then I know that from a to c, that amount plus c to b is going to equal the entirety from a to b. So we can break up our integrals and add pieces of them together to get full integrals. So let's look at this example. It is known that the integral from 0 to 10 of f of x dx is 17, and the integral from 0 to 8 of f of x dx is 12. Find the integral from 8 to 10 of f of x dx. Okay, so I'm just going to write this out. You probably could look at this right now and figure out what it is, but I'm just going to write it so we have it to see where everything's coming from. So I have 0 to 10, 0 to 8, 8 to 10. So I kind of want to order it so it makes sense. So the first thing, if I'm going from left to right, would be 0 to 8. So I have 0 to 8 of f of x dx plus the integral from 8 to 10 of f of x dx. If I add these integrals together, what I'm going to get is the integral from 0 to 10 of f of x dx. So I know that the integral from 0 to 8 is 12. 8 to 10 is what I'm trying to figure out. So I can keep that as the integral from 8 to 10 of f of x dx. And I know that the integral from 0 to 10 of f of x dx is 17. So I'm just solving it as if it was just like a variable. So the integral from 8 to 10 of f of x dx is just going to equal 5 because I'm going to subtract 17 minus 12. Okay, so you don't necessarily need to write it out if you can look at this and understand that's what it's doing, but we're adding integrals that are over adjacent intervals. Okay, just looking at one more similar to this. So again, you have an interval from 2 to 8, 2 to 4, and you're trying to find 4 to 8. So you can kind of set it up however. I'm going to always go from left to right. So I have the integral from 2 to 4 of f of x dx plus the integral from 4 to 8 of f of x dx. And that's going to equal the integral from 2 to 8 of f of x dx. Now, if you wanted to set it up with subtraction or however you see to do it, you can do that as well. Plugging in the stuff you know, we end up getting 2 to 4. This is going to be 5.9. This is what we're trying to solve for. So I'm just going to leave that like that. And then that's going to be equal to 7.3. So if we subtract, we get the integral from 4 to 8, which is going to equal 1.4. Okay, so now we're going to kind of put everything together, and we're working with these 3 pieces of given information. So evaluate the integral from 3 to 3 of g of x dx. Well, here's g of x, so we have to use this one, but it's going from 3 to 3 where the a and the b are the same. So from that property, we know that that's just equal to 0. Right? It hasn't moved anywhere, so there is no area under the curve. For b, we want the integral from 6 to 1 of 3 f of x dx. Now, I have a problem here because my limits of integration are not in the correct order. I have the 6 on the bottom and the 1 on the top. I need my 1 to be on the bottom. So in order for that to happen, I have to negate it. So what I'm going to do here is take out the negative, and then I'm going to switch it and make the limits 1 and 6. Because I have this constant of 3, I'm also going to pull that outside, and then I have f of x dx. So I know that the integral from 1 to 6 of f of x dx is 5. So I really have negative 3 times 5. So negative 15. Okay, and then we have the integral from 3 to 6 of f of x dx. Well, I don't have the integral from 3 to 6 as one of my givens, but I do have the integral from 1 to 3 and from 1 to 6. So I can say that if I take the integral from 1 to 3 of f of x dx, and I add it to the integral from 3 to 6 of f of x dx, I'm going to get the integral from 1 to 6 of f of x dx. So similar to before, we know 1 to 3, we know that's negative 2. This is what we're trying to solve for, 3 to 6 of f of x dx. And we know that the integral from 1 to 6 is 5. So now I can solve this, and I get that, I'm just going to write it like this, that integral is going to be equal to 7. Okay, and then the last two, again, based off of the same original 3 givens. Here we have the integral from 6 to 1 of f of x minus g of x. So we're subtracting, but we also have this problem of having the limits of integration reversed. So what I'm going to do first is just split it up. So I'm going to say this is the integral from 6 to 1 of f of x dx minus the integral from 6 to 1 of g of x dx. So I broke it into 2 separate things. But now I need to switch the limits of integration. So that means I'm going to have to negate this. So what I'm going to do is pull out a negative, and now this becomes 1 to 6 as the integral of f of x dx. And then here I have a minus, but I have to make it another negative in order to switch the limits. So this will now become a positive from 1 to 6 of g of x dx. So we have the the integral from 1 to 6, that's 5, but we have a negative, so we get negative 5, plus from 1 to 6 of g of x, which is over here, that's 7. So we end up with 2. And then for this last one, integral from 1 to 6, so we don't have to worry about negating anything. And then we're adding, and we also have this constant in front. So I'm just going to split it up. I'm going to take out the negative 2 and bring it on the outside because it's a constant. So I'm going to have negative 2, the integral from 1 to 6 of f of x dx, plus the integral from 1 to 6 of g of x dx. So here I get negative 2 times the integral from 1 to 6 of f of x, which is 5, and then the integral from 1 to 6 of g of x, that's going to be 7. So I end up with negative 10 plus 7, which is negative 3.